Our final topic we're going to talk about with entropy is the idea of heat engines. So the initial thermodynamic description of heat engines was described and was a big part of the development of thermodynamics back in the time of steam engines. And the similar ideas are still relevant to internal combustion engines and things like that. The basic idea is that we want to try and convert energy in the form of heat into useful work. And so the process by which this happens is that we have some sort of hot reservoir at a temperature TH. So this could be, something that's being heated by, a fire for our steam engine, right? We heat up the steam, that's our hot reservoir. Or in the case of our car, it's fuel-air mixture is combusted, and that generates the heat that drives drives our engine. But we want to turn that into some sort of mechanical work, and so that energy is input into our engine. And then we produce some amount of work, but we can't convert all of the heat into work. That would violate the second law of thermodynamics because that would overall be a negative entropy process. So what we have to do is some of the heat that's input into the system has to leave the system. So some heat comes in QH, some heat leaves QC, that goes to a cold reservoir at a temperature TC, at a lower temperature than the hot reservoir. So basically, a heat engine takes what would naturally happen, right? Heat would flow from the hot reservoir to the cold reservoir, and in the process, we try and get some work out of it. That's basically what we're doing here. And so one of the, so there was a engineer named Carnot, a French engineer, who wanted to examine these steam engines. This was back in the time of steam engines. And so he came up with a theoretical, idealized engine that is the best possible way you could do this. Happens reversibly, and so this is the cycle that Carnot came up with, and this is known as the Carnot cycle. And there are different kinds of cycles that are more applicable to things that are happening in engines that you're familiar with. So the Otto cycle, OTTO, is similar to a diesel engine, or that may be a gasoline engine. I can't remember which. But anyway, the Carnot cycle is sort of an idealized case. So what we have here is we start with a piston of some kind, usually. Something with a small volume here. We have heat enter the system, whether through a chemical reaction or through just having it in contact with hot steam or whatever, and that leads to an expansion. And in the idealized case, we do this isothermally. We let the temperature be TH, and that the expansion happens at that same temperature. Then we do a further expansion, adiabatic expansion, to let the temperature go from TH to TL without losing any heat in the process. So that's what makes this an idealized. And again, every step along this is reversible. So we get an adiabatic expansion. And then once we've gotten the adiabatic expansion to the low temperature TC, or in this case TL, then we do an isothermal compression that releases heat. And right in the process here, we've done some work. We've done some work here by letting the piston expand. And we have to compress back to the original. And then we have an isothermal compression and then adiabatic compression of a little bit further. What this looks like on a PV diagram over here is we start at state 1 here. We follow an isotherm here to state 2. Right, so that's our isothermal expansion. Then we have an adiabatic expansion down to the lower temperature. Then we have an isothermal compression, and then we go back to our original volume with the adiabatic compression at the end. So this is our overall cycle. And so at the between 1 and 2, we have things at the hot temperature, and 3 and 4 are TC or TL at the low temperature. And so the area inside of this is our net work that we were able to get out. The rest, and then because so you'll get some amount of work that's done in this isothermal compression or isothermal expansion, but you have work that has to be done to do a isothermal compression from step 3 to 4. So anyway, the area inside of that curve is the work that you get out. And so then the question is, what does this look like in terms of how much work can we get out? What's the efficiency of our engine? So we'll look at that in the next video.